Is it too annoying? Okay. So I'm going to speak on computing with sheaves and sheaf cohomology in algebraic geometry. This is a slightly different title than what I had in my description. I want to sort of put in more examples and not just do computing sheaf cohomology. So here's the thing. So the other day, Bernd asked me a question. He said, are you going to basically assume working knowledge of chapters 1 through 5 of Hartshorne inside and out, backwards and forward? So I said, yeah. No. No. So here's the point. What I want to do is, this could get to be really a technical, awful sort of thing, but it's also really cool. And what I want to do is I want to start sort of from the beginning, get you comfortable with the notions, and make this something very interesting. So there's a couple things. One is, if you do know all of those things, okay, then oftentimes algebraic geometers are routinely surprised that you can compute any of these things, okay? Well, other than the standard sort of ways one learns about computing, like using Mayer-Viedres sequences, stuff like this from algebraic topology. So for those people, hopefully they'll learn something. If you have a passing knowledge of sheaves and things like this, this is really good also, because then it sort of gives a concrete view of it so that you can understand that. And it's also useful stuff. And if you don't have that, well, I think you can still get something out of this as well. So we'll see how it goes. Anyway, that's this. So here I want to give a couple sort of situations that are useful. Oops, let's see if this is Okay, so let's just take a very simple situation. We are given equations for an algebraic variety, a nice zero set. I'm going to pretty much stick to projective space, as Bernd says, like projective space, okay? It's also where a lot of the theorems really come into their own. So basically we have x is, that looks very, is that better, or is that okay as far as fuzziness goes? Hard to tell down here. So at any rate, we have a variety x, or some algebraic set, given by equations, f1 through fr, which are going to be polynomials, homogeneous polynomials in the polynomial ring S. S for me will always be a polynomial ring, k of x0 through xn, where k is a field. And in fact, you can think of it as some algebraically closed field. You can think of it as Q, finite field. I don't really care a whole lot as it will turn out. But geometrically, it should be something large like the complex number, something algebraically closed. Okay, so suppose you have equations staring you in the face. How do you figure out anything about it? Well, for instance, if you want, you can use Grubner-Basic to give you a bunch of basic information. For instance, the dimension of x and the degree of x. These are numerical invariants that you can find. Well, now suppose you happen to know that x is a smooth variety, a non-singular thing. Let's see if I can. This thing wants to sort of snake that. We'll do this sort of thing. That at least keeps it sort of from going. Okay, so anyway, suppose x is a non-singular variety, which is a lot of times the situation you're interested in, and you want to find out something about this. The first thing you might do is, well, it's non-singular, so it basically doesn't have components that will intersect each other, because they would have singularities. But it might still be not connected. It might be several components. And this actually happens in practice. You're given equations. It might be too difficult to do sort of an absolute primary decomposition of the thing, introducing it, and you just want to know whether x is connected. Well, it turns out the cohomology will give that to you. And now it stays. Okay. So suppose now that x is maybe x is a curve. Whoops. X is a projective curve. You might be interested in other pieces of information, perhaps the genus. Actually, in this particular case, you can also get the genus from the Gröbner basis information. But maybe you're interested in actual rational function. Honestly, rational functions on this curve that has prescribed sets of zeros and poles. So for instance, if you're given points P1 through PR on your curve X, and certain multiplicities, positive or negative, and you want a rational function that has those prescribed zeros and poles. Maybe it'll have slightly more zeros than that or something like this. But in any case, one can zero in on exactly this problem as well. And again, there are several ways of doing this kind of thing, but one way is using cohomology. Okay. Well, suppose it's not a curve. Suppose it's a surface. Okay? So what might you be interested in a surface? Actually, a lot of these things hold also if it's a higher dimension than that. You might be interested in the actual topological, the drawn cohomology or singular cohomology of your surface. You might actually be interested in hi of x with coefficients in z, but that's a little different. Okay? So this is something that you can get from the algebraic side a little easier. Okay, so you might like that. You might also like the numerical invariance of a surface. For instance, the geometric genus or the irregularity. All of these have definitions in terms of cohomology and dimensions of cohomology groups. Another thing you might be interested in is you have your equations staring you in the face. Is X rational? Can you write it implicitly as a map to projective space? Well, it turns out that there's this really cool theorem, if you've studied any algebraic geometry, you might know, called Castelnuovo's theorem, which basically gives you a cohomology criterion for detecting that. And even better, in some sense, once you have that, it actually tells you how to, it gives you help in constructing a parameterization. Another cool thing that you can do is, if you have a surface, X, one of the best ways of studying it are by looking at curves on the surface and considering their intersection theory. So for instance, if I have the projective plane and I blow up a point. So that if I blow up a point, that means I'm replacing that point with all directions to it, which is a line. And so now I can look at the intersection theory on this. So that line intersected with itself has self-intersection -1. Or normally, if you have two curves, they intersect in the number of points of intersection. So you can actually get at this thing using cohomology as well, or actually you can do it without. You can actually get at that a little easier manner than cohomology, but it's the same sort of thing. So you can do intersection theory on your surface. And then you can use that to re-embed your surface or try to find interesting subvarieties on it. That actually works also in higher dimensions, but it's a little more complicated. So, another thing that you might be interested in, and this is actually related to the top thing that's almost off the board at the moment. You might be interested in the so-called Hodge diamond. We'll talk about this in a little while, in a couple lectures down the road. But if you have X, you can look at the sheaf of P forms and take its Qth cohomology. These things give you a really nice sort of display, numerical display of your surface or threefold or whatever it is. And you can, in the right hands, it can be really powerful. So at any rate, I'll give you a good view of what's going on. Okay. So anyway, so that's it. So basically, given a single variety X or something like this, you can use cohomology to sort of get a good picture of what's going on, either with the geometry on it, or with numerical invariance, or some picture of what's going on. Whoops. Now you can hear me. Okay. There's another important situation, though, that is used a lot in algebraic geometry, and it's families of projective varieties. Or there are a couple ways of doing this. One might be that if I take a variety X in say, a cubic surface or something like this in 3 space. It's migrating. But anyway, whatever. Okay, so I take this and I can move my surface around, deform it basically. For a hypersurface, that's not a big deal. I can just change the equations of the hypersurface, sort of like Behrens didn't care about his equations, his coefficients so much, and that would be similar. But if it's not a hypersurface, it's a little bit more challenging to do this, where you keep the geometry set. There's this cool thing in algebraic geometry called the Hilbert scheme, which I'm going to talk more about in a few minutes, because it's actually part of the project. And I wanted to sort of get it out on the first day of these talks. But anyway, so I'll talk more about that in a bit. Another thing you might be interested in, a lot of higher dimensional geometry these days is basically uses the following sort of thing. You find a curve on your surface, and you want to find rational curves or something like this. So there are all these ways of bending it and squashing it around until you break it into smaller pieces, which are hopefully simpler. Then you take that and you continue doing this. So what you really need to do is know if you have some curve on your surface, or a threefold or something like this, how it can move around on it. And again, you can use cohomology to sort of figure out this kind of information. And you can do it in 2 ways. So you can use the cohomology the way a lot of algebraic geometers is. They just get the numbers out and hope and only consider the cases where they're non-zero, or when they're 0, or when something nice happens. And that actually tells you an awful lot, but then you can also use them in a more subtle situations. Not that we will do that here, but you can do that. Okay. So anyway, basically, the whole point of all this then is that it's cohomology to the rescue. All of these kinds of questions can actually be computed using, or at least get useful information about these kinds of problems by using cohomology. And the fact is that you can actually compute these things. It's really, I don't know if you've ever seen the definition of cohomology that Hartshorne gives. It's really whatever you want to call it. Okay, so basically you take a sheaf, you take an injective flask, resolution of this sort of thing. Just this huge, each term, if you actually try to figure out what it is, has an uncountable number of summands to it. It's impossible to actually write down. And so if you see that, you say, there's no hope of ever being able to compute these things. But it turns out that way at the beginning, Serre, who was the first computational algebraic geometer of the modern era, had sort of figured out how to do a lot of this stuff before it sort of got changed. Anyway, I don't mean to put down all the other stuff, but the thing is that you want to be. The stuff is a lot more concrete than it actually appears at first glance. Now, what I want to do before getting into, let's see, I started at 11:30, right? I'm going to do the following example. I'm going to do a Hilbert scheme example. So this is pretty cool. So this, Stop. Okay. So the Hilbert scheme of the twisted cubic curve. So the twisted cubic is one of these examples that lots of geometers use. It's a curve in projective 3 space, which is defined by these 3 polynomials. I'm using A, B, C, D instead of x1, x2, x3, x4, or something like this. Just, I don't know why. Just to get rid of subscripts. Because, it's hard when you're taking slides like this. So anyway, B squared minus AC, BC minus AD, and C squared minus BD are my equations. Okay. Now what let's finish this slide before we go to the next one. Okay, so the Hilbert scheme of anything. So I has a given Hilbert polynomial. Are you familiar with Hilbert polynomial? Basically, it's in each degree. You have the dimension of the ideal, actually the dimension of the polynomial ring modulo of the ideal. And for high enough d, this is a polynomial. In this case, the polynomial is 3d plus 1. D is not the same D. That was unfortunate. It's 3z plus 1, or something like this. Okay, so it's just a polynomial of degree 1. The 3 it means that it has degree 3. The plus 1 actually means that it has genus 0. Right. Anyway, so that there's this Hilbert scheme H, which parametrizes all subvarieties or subschemes or whatever that have basically all ideals. It's actually saturated ideals. I don't want to get into that, but basically whose Hilbert polynomial is exactly 3d plus 1. Okay? So for instance, some points on this Hilbert scheme are the following. Well, the ideal x up there of the twisted cubic, that's one, because we started with that one, basically. Okay? Here's another one, b squared comma bc comma c squared. If you actually calculate what the Hilbert polynomial of that is, it's also 3d plus 1. And so it's also there. And here's another one that's a little interesting. It has a linear form in it, a, b to the fourth, and b cubed c. This is an ideal example of a monomial ideal, which is a so-called lexicographic ideal, which basically means at each degree it has if you write all the monomials in each degree, they're the first ones in lexicographic order. Okay? And those are kind of interesting points. Okay, so anyway, those are some points on that thing. There's actually two things over here that I want to say. So let's actually draw a picture of this first. Here's what this Hilbert scheme looks like. This was actually first, I didn't write this down, but this was first done by Pini and Schlesinger sometime in the, I forget if it was in the late 70s or early 80s. I think it was late 70s. But in any case, it turns out that this H here is that it's always an algebraic scheme, actually. It has lots of components usually, and sometimes they can be non-reduced or just nasty in other ways. So this has two components. It has a dimension 12 component where I sub x, so remember my points on this are the ideals or the subvarieties or subschemes with this Hilbert polynomial. So I sub x is one of them. Here's another one, b squared, bc, c squared. There's the lexicographic point over here. It's actually on a different component of dimension 15. And then there's this little guy in the middle here, which actually, this monomial ideal here has also the same Hilbert polynomial, and it's on the intersection of these two components. And you can sort of go through and sort of figure out various things about this if you wanted to. But here's a cool thing about Gröbner bases. A Gröbner basis actually gives you a path on this Hilbert scheme. And so here's how this goes. This is actually closely related to what Bernd was saying. Let's see. What I do is I take my ideal. So t is now a parameter. I'm going to have a family, one for each value of t. And this is where the whole family stuff comes in. It's b squared. I'm actually scaling the variables. I'm leaving b and c alone, and I'm scaling a and d by t. Okay. So actually, I'm getting something that's isomorphic. The only difference is that I've just scaled the variables. So geometrically, it's pretty much the same kind of object, except at t equals 0. At t equals 0, I get b squared, bc, c squared, which is the initial ideal of monomials, the Lie term of that thing. And in fact, these the powers of t are exactly the expense that Bernd was talking about in his lecture. So that how cheap or expensive it is the power of t that you have on that. And so the Lie terms are the ones with the least power up there. Okay? So I sub 0 is this b squared, bc, c squared. I sub t is up to scaling the same thing as I sub 1, which is the ideal x. And basically, that's a nice family. They all have the same Hilbert polynomial, and it gives you a path on it. You can think of it as a path from Ix to the monomial ideal b squared, bc, c squared. But in reality, it's a whole sort of thing. Question? Yes?
You mean this is the same ideal?
I sub x is not, I sub 1 is the same ideal, I sub x.
You had IT equals I sub 1.
Yeah, what I say IT is equal to up to scaling. So up to a change of variables, it's the same thing. So it's only isomorphic in some sense. It's not the same. If it were the same thing, it would be exactly the same point on the Hilbert scheme. But it's sort of in a minimal way different. Okay. Here's a theorem that relates the cohomology, and this is actually used a lot now in the sort of higher dimensional algebraic geometry. It's used in various forms that are related. So suppose I take a projective variety, or scheme, it doesn't really matter. As long as it's projective, it sits inside a projective n space. And it has a Hilbert polynomial P of D. And let's let H be the corresponding Hilbert scheme, this H. It has lots of components, that one had 2, and so on. Then it turns out that using cohomology of something of this sheaf N, which we actually will be talking about a bunch later on, even later today, that the tangent space of the Hilbert scheme is exactly this H0 of this normal sheaf, of this thing, which is really pretty cool. Means that these things are hard to construct, these Hilbert schemes. I mean, you can do it, but they're in high dimensional spaces, and you have to sort of work hard. This is a very simple way of just getting your hands on the dimension of the tangent, Zariski tangent space. Okay. Now, it turns out also that if X is say a smooth variety, okay, or it can be a little more general, a local complete intersection, if you know what that means, but otherwise think smooth, non-singular, then actually every component of H through this point, okay, so there we had a 12-dimensional and a 15-dimensional through that one point. Well, that wasn't a local complete intersection, but suppose that we have something in there, then the dimension of every component going through is at least as large as, well, the dimension of the Zariski tangent space minus H1 of the normal bundle. So the dimension of H1. We'll talk about all those things later and try to understand them, but basically this is just to get an idea that these things actually are measuring something interesting. And in Kolar and Maury actually really, as part of his Fields Medal stuff, sort of generalized all of this and got really nice, precise statements, and used it to sort of forge the whole threefold. Well, this is one part. Okay, so anyway, so this is the thing. This is one thing. So now, okay. So here's another picture of it. It's a family, so it's sort of moving. No, actually, this is supposed to be the family itself. So anyway, so we have I sub x here, and it turns out, and actually Pini and Schlesinger prove this, but you can actually do it by computer without any work. You can just actually write down the equations of these things, and you see that this component here is basically a dimension 12. It's a smooth, rational variety. Okay, about as nice as it gets, except it's dimension 12. And this is dimension 15, and it's also smooth. And in the middle, they intersect along a dimension 11 component, and it's a transverse intersection. Okay? And sure enough, and the dimension of the tangent space at that little point there is 16. So it has to be larger than either of the two dimensions, since it's singular at that point. So anyway, so part of what the project is going to be is going to try to understand the structures of at least the local structure around certain points, like simplicial complex ideals, or certain monomial ideals, or something. These Hilbert schemes. There's a lot that can perhaps be said. Notice that this lexicographic point, by the way, I can't resist but to say this, even though I don't know how much it has to do with anything, except for the project, perhaps. The lexicographic point is in many ways the worst point on the entire Hilbert scheme. Okay, it's got I don't know. It's just it has the highest what's called Castelnuovo-Mumford regularity. It's sort of just a bunch of things that are about it that are just really bad. And we always used to think that this thing had to be the most singular point on the Hilbert scheme. Way down deep and lots of components. Really nasty. But in fact, it's a smooth point here. Okay? And it turns out that that's not an accident. So this is just something that my student some years ago, Allison Reeves and I proved, that if you have the lexicographic monomial ideal, I better say it fast. Okay. So if you take a lexicographic monomial ideal with the given Hilbert polynomial, okay, then that is a non-singular point on the Hilbert scheme. So there's always, it's sort of far away from anything nice, actually, from anything geometric. But anyway, it's still a smooth point. I want to just show you a Macaulay 2 computation now that actually sort of does this. We'll go on later and understand it a little bit better. Now let's see if I can do this. Let's put it on. And we'll see if that actually does it in a second. Is this stuck? Okay, now wait, did I have to do anything else? It's still flashing on. Yeah?
Well, that's loading. What does it mean by the lexicographic?
Yeah, that's a good point. So, in fact, there's a lot of different, there are a lot of different lexicographic ideals with a given Hilbert polynomial. They can have different Hilbert functions. So, for instance, if I take an ideal, any ideal, and I truncate it in higher degree, like take the twisted cubic, and now I look at all the degree 3 polynomials, and that's generated by degree 2 polynomials, and I look at the degree 3 things, okay? Those two actually define in projective space the exact same subvariety. But they have different Hilbert functions. They have the same Hilbert polynomial. So here you can have different lexicographic ideals having different actual specific dimensions of these spaces. But there's one saturated one, if you are familiar. I'm not sure that helps a whole lot. But anyway, you have to look at the saturation as you remove the component at the maximal ideal x0 through xn, which is it doesn't ever enter into there are no zeros of that in projective space. So it's sort of like it's just flat. Now, let's see if I can, actually, are there any other questions before I do this? This is a good time for questions. Okay, so let's see if I have this right. Nope, I don't. Wait a second. I have to start at the beginning of my example. Well, it wants to start down there for some reason. That's okay. Okay, so I'm going to, actually, is there a way to turn the light off? I see, this is just fun. Can you all read that? Okay. So anyway, making a polynomial ring in 4 variables, we're just going to consider the twisted cubic for the moment. And I'm going to make this ideal here be, the twisted cubic ideal. Okay, now I'm going to explain this all. You'll sort of understand it and also why this is it. But this hom of I, comma, s to the 1, that's really s mod I, that's a module whose sheaf, which we're going to talk about what this all is, but that's the sheaf corresponding to this nice little module is actually the so-called normal sheaf that we were just talking about. And here is what it is. It's the co-kernel. It corresponds to a module which has 6 generators, and each of these columns is a relation on those 6 generators. So if you call the generators E1 through E6, the first one is B times E2 is equal to D times E6. Okay? Who knows? I mean, what this really means. You have to sort of sit down and actually figure it out. But in any case, that's the sheaf that corresponds to this, or the module. And now you can calculate H0 of this sheaf. And it uses one of the techniques that we're going to talk about to do that. And it comes out with a 12-dimensional vector space, which is pretty cool. Works because that was the dimension of that component, okay? So since it's smooth at that, you would expect the dimension of the tangent space to be exactly equal to the dimension of this space, which is 12. H1 of n it should be basically sort of the obstruction to smoothness. Remember, so basically every component will have dimension greater than or equal to 12 minus this number through that point. Anything through that point. And that dimension is 0, which means that, in fact, this is a smooth point. Okay, without doing any sort of time to figure out the equations of it or anything. Doesn't always work out that nicely. But in any case, here's a second one. This is the lexicographic point. Okay? I'm doing this, I take the ideal A, B to the fourth, B cubed C. Now I'm going to do something, a slightly different way of doing it. I don't know why. R is S mod I. That's the ring. I'll show you why I'm doing this, okay? This is another way of getting the idea. We'll talk about this actually later as well. This is just sort of intro kind of thing. This is getting the ideal I as a module over the ring R. So you're tensoring I. Star star is tensor product with the ring R. Don't worry about it so much. That's that. And then you can take the normal sheets. This is just a different way of computing it, perhaps a little more obscure. Okay? But we'll get to that. And you have this is your n, just like we had before. Now there are 4 generators. The -1, -1, -1, -3 has to do with what degree these generators are in, which is actually important information, as we'll see later on. Anyway, so the first one is the C on the first column says that the first generator times C is 0, whatever that might mean. We calculate H0 of this, and it's 15 dimensional, which is the other side. We calculate H1 of it, and that's 0. That H1 actually doesn't mean a whole lot, although it turns out it does, because that's not a local complete intersection or a smooth point, like I said. There is a way of doing this, which we're not going to talk about in these lectures, but I just want to sort of show you. There's something called global X, which is sort of generalization of cohomology, and Hartshorne makes that one even sound worse than the first one, okay? But it turns out that's also easy to compute. And so here it is, x1 of the ideals, the sheaf I, and into the O of x, basically, which we'll talk about. And that's 0, which means that there's no, that is a smooth point. If that came out to be non-zero, though, it wouldn't say anything. I mean, it could still be smooth or not. It's just there's just this bound of dimensions. We'll see. Is there anything else I wanted to do with that? Probably not. On intersection. Oh, this is the point in the middle of the intersection. I'm doing it the same way. N is the sheaf. It's a little more complicated, but not too bad. It's all monomial-ish things. H0 is 16, like we saw. H1 of that is 0-dimensional, but it is. But the x1 that is bounding the dimension is 4. So every component has dimension greater than or equal to 16 minus 4, which is 12, which is exactly correct in this case. There's a 12 and a 15. Okay. Anyway, so that's some of the stuff that you can do. Okay, good. So that's enough of that. Let's see if we just get that off. Okay, that's the intro. Okay, so basically, cohomology, you can actually compute with it, and it actually is something that you can really use, and it means a lot of cool stuff. So now the question is, how do you actually compute it? Well, we're going to start by not computing it. We're going to start by looking at algebra. Okay, let's see. Wait, which was the last one? The whole thing that makes all of this work are physigens. Yeah. Okay, there. Okay? Here's the key computation that is used all the time in computing every one of these sorts of things. Is suppose I have a matrix over a ring R. The ring R here, by the way, is usually just the polynomial ring, or maybe the polynomial ring modulo an ideal. Okay? One of those two things. So you just want to find a generating set for the kernel of that. Okay? That's all. So you just want to do a little bit of sort of homological algebra. And what was really cool about this several people actually, Frank Schreier was one of them, this guy David Spear, and a couple others I think also over time found it. But basically, if you use the Buchberger algorithm, or basically any algorithm for computing Gröbner bases, then it automatically, if you just keep track of enough stuff, you get a basis for this kernel. So in other words, you can find, you find the Gröbner basis of the image of F. Actually, this is a good point. Let's see, do I have anything? Let's see if my next, yeah, good. I'm thinking of this matrix, RB to RA, is an A by B matrix. So each column is one of the image vectors of and there are B of them. Okay? And basically, those are a bunch of elements of R to the A. There are B of them, each of those columns. And that gives me some set of vectors. And if you calculate a Gröbner basis for that, we're going to do an example in a second, then actually as a byproduct, you get this curve. Now, okay. So here's the twisted cubic curve again for the moment. And so here's, okay, so again, F1, F2, and F3 are our three generators. Turns out that if we choose a monomial order where B squared, BC, and C squared are the lead terms, this is already a Gröbner basis. Okay? So those are all the lead monomials that you could possibly get by any sort of combination of these three polynomials. And the kernel of, and so then F, the map that corresponds to that, is just the map from R3 to R given by those three polynomials. And the kernel of F are the triples of polynomials which dot to 0 with those Fs. Okay? So that's what syzygies are these modules. Okay, let's take a look at the Gröbner base, the Buchberger algorithm for this. How does the algorithm for computing a Gröbner basis work? Some of you probably don't know, since I'm just asking this morning what the definition of a Gröbner basis is. So here it is. Okay, the way it works, at least roughly, is you take every pair of your polynomials in your tentative Gröbner basis, and then you'll be adding more if it doesn't work. You actually cancel the lead terms. Okay, so B squared and BC, you can cancel the lead terms by multiplying the first one by C and the second one by minus B and adding. And when you do that, you get another polynomial now in degree 3, and you can look and see if you can sort of subtract off some multiple of any of your elements in your idea. You reduce it, or you find the remainder with respect to the polynomials you have. So in this case, what is it? If I take C times the first minus B times the second, I get minus A C squared for the first, and then what is it? Plus ABD. That's A times the third one, I guess, or minus A times the third. So if I add A times the F3, I actually get 0. Okay? And now it's a Gröbner basis, and every time I do this operation, I always get 0. So here I have 2 of these things. Actually, there's 3, but it turns out you only need to do these 2. But here, look at this. If you keep track of what you're doing, you have syzygies. You have elements of the kernel. You have C minus B and A, which is this guy here, C minus BA. And you also have the other one, C minus B minus D. Minus D. The F1 is first, and then F2, F3. Okay, so you have minus D, C, and minus B. Okay? So as a byproduct of the Gröbner basis computation, if you keep this information around, you get a bunch of syzygies. Oops. Where's my... Okay. This one will be said. My slide has gone, has decided to hide. But basically, here's the idea. Is that what Schreier noticed, and a couple other people, is that if you do this process, these set of syzygies that you get actually generate all of them. So this generates the module, absolutely all of them. So this is really cool. You know, I first got into this actually as an undergrad, doing some computer programs for Graham Evans. And we didn't have this kind of techniques. We could only do syzygies degree by degree, and we had to use all these theoretical techniques to try to see if we had them all. And it was actually very hard to tell. And sometimes we got it wrong, and so on. And it seemed like there was no really good way of figuring out what degree you had to go to find all the syzygies. Because it turns out there's these really bad examples called the Mayer-Meyer examples, where if you have your original generators here are degree 2, but say they're degree, actually even 4, you can have, or even 2 for that matter, you can have the syzygies occurring in degree essentially 2 to the 2 to the number of variables, and which is really dramatically bad. Okay, but nonetheless, and it just says that it would be very hard to compute that particular Grosvenor basis because as a byproduct, it's giving you all of this. Okay, anyway, so that's that. Now, I'm missing one of my slides. That's it. So now I want to do a little aside. You Paul mostly know this. By the way, if you ever want me to slow down or speed up, you can tell me. Same as the other guys, okay? So this is just a little aside on graded modules. Yes?
So I have a good question possibly. So you said, so this is a byproduct of Grosvenor's algorithm, which gives you a Grosvenor basis, right?
Right.
So how is this, how is this giving you a Grosvenor basis? I mean, what is the algorithm actually doing?
Okay, the algorithm, so in this case it's already a Grosvenor basis, but supposing it were not, what would happen is one of these things you would not be able to add elements of your polynomials that you have already to reduce lead terms, and you'd just be stuck with a new polynomial. If you're stuck with a new polynomial, you throw it back in the Grosvenor basis, and now use that for S pairs. The analogy that I like is something that my friend Dave Beyer always said. Doing a Grosvenor basis is a lot like snow blowing. So you take a snow blower, there's snow all the way here. Instead of pushing the snow this way, you push it straight ahead of you. And you just keep going, and you're piling the snow up higher and higher. Because you're getting more and more Grosvenor basis elements, and as you do, you get more and more S pairs that you have to check. And it just sort of gets worse and worse as you go, until finally you're done.
So,
yes?
So how do you know when you finish A, when you finish, and B, how many linear combinations of this sort do you have? How many?
Right, how many of these do you have to take? The short answer is, and there are a bunch of optimizations that you can do, but if you take all of your polynomials, and in this case, you can always cancel lead terms because they're not vectors. Okay? If they're vectors, then you have to be able to cancel them, which means that the lead term has to be in the same row. But anyway, so here you take all pairs, and you cancel lead terms as minimally as possible, like you do here. And then you reduce that with respect to what polynomials you have. Okay? And if you always get 0, then you've got a Grosvenor basis.
So you have to do it for pairs.
You have to do it only for all pairs. But it's a lot. But it turns out you don't actually have to do it for all the pairs. You have to do it for, well, anyway, there's several ways of improving it. Still, there's a lot usually. Okay. Now let's see, where was I? Oh yeah, so here, this is just a little aside on graded modules. So S is a polynomial ring, and we're always taking it, since we're doing the projective space, the degree of each xi to be 1. Okay? So I didn't write it, I forgot to write it, but S is really, S sub D is the degree D, the vector space of degree D forms, okay, in the polynomial. And M is just a graded S module. If you can take a direct sum over K of these M sub Ds, such that when you multiply M sub E by an SD, you increase the degree. So you can give it a So anyway, just want to not, this is just, I expect a lot of you know this already, or probably inside out, but some of you might not, and if you don't, I don't want, the rest will be hard to figure out without what's going on. Okay. Here's a cool construction. Sayre first did this, I believe, is that, and I think that he got the direction wrong. But anyway, it's just annoying. So M of E, so M, if I have a gradient module M, and I do this E here, that is the same S module as M, okay? I'm not changing the module at all. It's exactly the same, but I'm going to change the grading of each element. So it's the elements of degree D in this new module are the elements that used to be of degree D plus E. Okay, well, here's the example to sort of drive that home. S of minus 3. It's still S. In other words, it has a single generator as an S module. But now the generator is in degree 3. This is why I think you got it wrong, because you're always now, we're always stuck. All of us doing this kind of thing are stuck writing negative signs here, all over the place. So S of minus 3, actually, its generator is actually in degree 3. Okay. Now, let's see, how are we doing here? Okay. So the one algebraic thing that is very cool that we need in order to compute cohomology, or pretty much anything in algebraic geometry, it seems. Well, that's not quite true, but a lot of things are free resolutions. Free resolution is basically you take your generator matrix, F1, F2, F3. R here is somehow S is migrated to be R, okay? But it, anyway, so here you have your generators F1, F2, F3. You take the kernel of that, and you take a generating set of the kernel. Well, we already saw the generating set. It's the two columns of this matrix in the middle here. So we make this an exact sequence by taking the R2 and mapping it to that R3, so that the kernel is actually equal to the image, which is generated by those two columns. Okay. And then, if you figure it out, that map D2 there has kernel 0. There just can't be anything else. So this is what's called a free resolution of R mod I in this case. And it's a minimal resolution. You can define it in several different equivalent ways, but in this case, since everything's nice and homogeneous, I want every entry to be homogeneous to some degree, and I don't want there to be any non-zero constants, like any ones or something. I don't want. If that were the case, that would probably mean that I didn't have a minimal set of syzygies. I threw in some extras. So I want it to be minimal, meaning that there are no non-zero constants. There can be zeros in there, but not anything else. That's that thing. Now, in terms of the applications of the cohomology and things like that, we really need to keep track of the grading, because the degrees are like really crucial sort of piece of information. So what we do here is we actually make this thing graded of degree 0. So think those F1, F2, and F3 all have degree 2. They're all degree 2 polynomials. Where is my ideal, actually? Here's the ideal that we have. Okay, those F3. So those 3 are degree 2. So if I want this map from R3 to R to be of degree 0, I have to give the generators degree 2, so that they'll go from there. The generator will go to a degree 2 thing. And because of this S of minus 3 thing, I have to, well, R here, I have to make it minus 2. Similarly, these things are linear, so the degree here has to be 1 off from that guy there. So it has to be not degree 2, but degree 3. Okay? And so this is called a graded free resolution. Any questions on that?
What if the original S were all the same degree?
Yeah, if they're not the same degree, which we will see examples, then this middle term here would be something like R of minus, if it was 1 quadric and 3 cubics, for instance, it would be R of minus 2, direct sum R of minus 3 to some number of the cubics. And in fact, that'll happen most of the time. You won't get them all the same degree. Okay. Let's see. Okay. There's this really cool theorem that Hilbert proved in 1890. Actually, this is, these days you can prove it in a second once you know a little homological algebra. You can just use Tor and a couple properties and so But at the time, he didn't even have the notion of exact sequences. And so it's really... Stop. Okay. So here's the theorem that he proved. Suppose I... Well, actually, this is at least the form in the case that we're interested in. Suppose I take the polynomial ring. Not a quotient polynomial ring. It's very different there. But a polynomial ring. And I take a finitely generated, graded S module. It doesn't have to be graded for the thing that we did, but we are taking it. Then if I take a minimal free resolution, it has its length, by the way, is what's called the projective dimension of M. That has to be less than or equal to the number of variables, n plus 1. And his proof is actually extremely clever, but not for the faint of heart in some sense. It's a lot of resultant theory. But he gave an algorithm for computing syzygies using resultants and things like that. It's not particularly efficient. But in any case, the fact that this is finite is really extremely important. He did this to prove that the Hilbert polynomial, the Hilbert function was a rational function, so that you can actually get a Hilbert polynomial. Then he goes on and proves stuff about finiteness of invariance of groups. All in one paper. It's just, basically does all of commutative algebra in one paper for polynomials. So. Okay, so let's see. Let's leave that example for later. Here's a good example. By the way, that's a good example that's a good thing to try to prove if you know anything about Tor. But actually, you can do this one using equivalent bases too. It's very cool. But we're not going to do that. Here's an exercise that sort of makes everything sort of effective in what we're talking about here. Okay, so assume that the ring R is either the polynomial ring or it is a quotient of that polynomial ring. And for us, it'll always be a quotient by a homogeneous ideal. But in reality, you could prove this without that. And suppose that we have some finitely generated R modules. Okay? By the way, how should you give a finitely generated R module? You have to think about it. What's the best way of giving it? One way, let's see, what's a good way? Generators and relations. That's a good way. That's a matrix, right? So the rows are just like we had before, are the generators, and each column gives a relation. So that's a presentation matrix. So giving a module by presentation matrix is a good way. Although not all modules are nicely given that way. For instance, an ideal, you might want to just give it by the set of polynomials. So you have to think about what you want here. But in any case, here's the exercise that assume that you can calculate syzygies. Over a polynomial ring, and then you want to compute this. You're given a map of modules from M to N. Part one of the exercise is to figure out how you give that. Okay, but anyway, it's just a matter of unwinding the definitions. It's actually good practice if you're not that familiar with modules. And then I want to construct generators and relations, essentially, presentation matrices for the kernel of F, or maybe the set of generators for the kernel of F, and the image of F, or the co-kernel of F. Some of those are pretty easy. Or image of F, I could just take the generators of the columns. But you have to think about what you mean. Anyway, so that's one thing. The kernel of F is the hard one there. And then the other one is, suppose you have a complex, M to N to P, so that the composite is 0, then I want you to construct the kernel of G mod the image of F. Okay? So this is, and this then basically gives you homological algebra at your feet. Okay, you got it by the, except for one little itty bitty problem. It doesn't do anything related to injective modules, like I was saying, because those things are horribly non-finite, and it's an interesting question how to deal with those. But this doesn't do that, and we don't need that, thankfully. Okay, so anyway, that's the end of the first lecture.